Hello, my name is Matt Holliday and welcome back to my class on programming in Go. So what I want to talk about in the next segment are Go's structures or struct types. And with that, I'm also going to dive into how Go does JSON using an interesting new feature of Go called struct tags. Okay, so I'm going to work in the playground for most of this. We'll have a couple of slides. And I'm going to start off by actually showing a struct. But I want to answer the question, what is a struct? We've already seen a couple of complex types built into the language. So slices allow us to have a sequence of one type of thing. And maps allow us to have sort of a key value table or key value lookup from one type of key to one type of value. A struct is an aggregate of different kinds of types usually. And so we have this thing that has fields, and we get values by looking up a field name, and the fields can have different types. Sort of the prototype of the notion of a struct is a database record, right? So I could have a record with an employee and the employee's boss and when we hired the employee and so on. And that kind of data of different kinds of information can be put into one aggregate structure to represent the employee. And so that's what I have here in front of me, right? I have an employee type, and I'm just going to go ahead and create an empty employee and print that. And so the standard %v gives us some curly braces and some stuff inside, no commas and no quotations. So the name is an empty string, and if we look down here, the empty string will just be an empty string. Okay, so there are a couple of options here on %v. We've already shown %v, but structs have another choice. There's something called %+v. And so if I put a plus here, it's going to go ahead and give me the field names for my struct in this output. It's still not quite as complete as the %v, but it does give me the field names, and that's a little easier to read. Now, let's suppose we want to put some data in here. Okay, well, one way to do that is actually to go in here and start filling fields with dot notation. Okay, and that's how you access the field of a record. So we could say, you know, the name is Matt, and the number, of course, has to be 1. Okay, and I'm going to use a utility function and just assume I hired myself right now. I'm not going to put in a boss right now. And I'll run that. And I forgot my closing quote mark. Let's try that again. Okay, so now I have my name, my number, boss is still nil, and hired now shows some date. Okay, and because this is the playground, we don't get actually now, we get some default time in the playground. That's not real, but that's okay. So that's one way to build up a record. Now notice I didn't put a value into every field. I don't have to. So instead of using dot notation, I can create a struct literal. Now, it's going to be a little bit different because I had var e employee, but what I'm going to do now is I'm going to put an equal sign there, and I'm going to create a struct literal of type employee. And if I run that, it's going to be, well, it's not going to be empty because I still have this. Okay, so let's get rid of that. And now I should still get the empty struct, and I'll put fields in it. But if I do that, I'm going to have to fill in all of the fields because otherwise it's the Go is not going to know where to put which things. So I can give every field in order and do it that way. And if we run that, I've got data. But I also have the choice, and I think this is better style, to give the explicit field names in the initializer. And if I do that, I also have the choice that I can leave out fields that I don't want to initialize. So now I can put in just the 3 fields I want, okay, by name. And in fact, I can give different orders, but I don't do that. I think that's confusing. And run it. And there we go. So we're back to where we were. Okay, so that's one way to do it. Of course, I don't need the var now, so I could just get rid of the var and use a short declaration operator, and I get the same thing. Okay, now, this is one case. I want to point out one thing here, and that is, so typically the employee hierarchy at a company is a hierarchy. It's a tree structure. And so, employees have bosses, or bosses have underlings, okay, in the Dilbert world. So an employee can have an employee within it, but not by value. I have to have a pointer to another employee. And that's what I've got here with boss. So boss is a pointer to an employee, and I'm allowed to put that in here while I'm declaring my employee type. So a type can refer to itself as long as it does it through a pointer. Okay, so now I could actually go in here and create another one. And I can also do it all in one line. So, I can put in a boss name, and do it all on one line, and now I've got that. Now I will have to do something with that or the compiler will complain, so we'll just print them both. All right, and now I have two employees where I can now go back and say, hey, by the way, e.boss is equal to b, and ask what that looks like. Well, but it has to be a pointer, so I have to put the ampersand that says yes. All right, that was one way to do it. Now, unfortunately, when boss prints out, it's just a pointer. So this is not going to be a terribly exciting way to print out the embedded data, because what boss is, it's a pointer, and I just get a pointer in my output. Now, there's another way to do that. I could have made b be a pointer by putting the ampersand in front of the employee, and now boss can just be b because it's already a pointer. And it's perfectly okay to do that. There are cases where I always want to have a pointer to my struct, and so I can create my struct, in a sense, anonymously, take its address, and then put the address into a pointer variable. Okay, so I've about exhausted what I want to do with employees except for one thing, and that is I can create my company, and we'll call my company a map of string to employee pointers. All right. Okay. Now, what I could do is I could now, instead of doing it this way, I could say that the entry for Matt is going to be this one, and the entry for Lamine is going to be this one. And I need to do something else now. So actually, I'm going to create them in different orders. I'm going to create the boss first. There you go. Because now I can come in here and say, my boss is the key that I found looking up the boss name, Lamine. Okay. Now, when I print this out, I'm going to get the same thing. I need an empty map, sorry. And I need ampersands. And I no longer have E and B. So we'll just go ahead and print these out this way. And we get the same sort of results, right? One has no boss, the other one has the boss that's a pointer. And that's not, again, that's not the best thing we can do. But to show you how to better format these things for output is something I can't get to right now, because we're going to talk about object-oriented programming a little later and how to put methods on things. I can create a method that will actually format this better, but I'm not going to do that just yet. Now, notice one thing about our map. It's a map of employee names to employee pointers. I don't have to do that, okay? I could take out the star and I could just use those, but there's a gotcha, okay? And the gotcha is this. Let's suppose I do that. And so each one of these becomes a value. And when I do this, that's still fine, okay, except, well, I can't do that, right? Because the employee I get back from looking up Lamine in the employee table or map is a struct, not an address. So what I want to do is I want to put the address operator in front of it so I can store a pointer to my boss. And you know what? Unfortunately, that's not going to work. Okay? So, and this is something I didn't really talk about before with maps. Because when we think about maps on a lot of types, we don't really care. But once you get into maps and structs, you say, well, I've got a map and it's a map of structs and I want to do certain things with it. And now we realize there's a limitation on a map. And that is, you cannot take the address of a map entry. That is to say, when I do a key value lookup, I look up a name, I get an employee record, it's a value, but I can't take its address. And the reason for that is because anytime I do a map operation, if I insert something into a map or delete something from a map, the map can rearrange itself internally because internally it's a hash table. And that hash table data structure is dynamic. So it's extremely unsafe for me to keep the address of an entry from a map that I get this way, because that address could turn out to be bogus, right? I add a few more employees into the map and suddenly the map rearranges itself and my pointer is a stale pointer. Now, it might not become a dangling pointer, but it might be a pointer to a piece of data that's out of date that nobody else in the map ever sees. And I'll explain that a little better also when I talk about this kind of problem with a slice. All right, so you can't do this, and that, because you can't do this, and there's something else you can't do, right? Let's suppose that the employee number is something I actually want to change. So let's suppose I look up Lamine and I get his employee number and I say I want to do plus plus. Well, you know what? You can't do that either. For the same reason. It's the same underlying reason. Now, you look at line 19 and you say, well, that ought to work because I'm not keeping the address. I'm just getting the address long enough to do this plus plus operation. Okay, and so there's an issue in the Go issue database, 3117. I almost thought about getting a t-shirt with the number 3117 when I first looked at it, because it seems like that would be really simple to fix, and actually it turns out it's not. The whole problem of how you can get access to a map value in a safe way to do this, what I'm showing on line 19, well, it's tougher than it looks. And so actually, this is probably something that's going to stay just like it is. So we can't take the address of a map entry, and also if I have a map of structures and I want to do something to a value inside that structure, I generally can't. And for that reason, you're almost always going to see a map of string to struct pointers, which is fine because I'll tell you something else. Now, if I do that, all right, I need to go back here and put in my missing ampersands. And I need to take off this ampersand, and now I can run it and we're good again. Okay, and oh, by the way, yeah, I incremented that number. Now that increment works because I no longer have a struct in the map, I have a struct pointer. And from an efficiency standpoint, it doesn't really matter because if you think about the map, if a slice is dense, we line things up in a row. If I had a slice of structs, it would be one struct after another. But when I have a map of structs, they're already all over the place. And so having pointers to the employee records is not that big of a cost on top of that. Okay. So I wouldn't necessarily want to have a slice of employee pointers. I'd rather have a slice of employees. But a map of employee pointers is okay. So I want to do one other thing here. We're going to move on and look at a slightly different version of this. I'm going to get rid of employees for a second, and we're going to do records, albums. Right. And we've actually seen something like this before. Right? So album is an anonymous structure, but actually I'm going to go one step further. That what I had so far wouldn't have compiled. but I can also initialize it. And again, if I'm going to do this, I have to give it all the values. Some ridiculously large number. I have no idea, right? And if I run that, it should run. I missed a couple of commas. No, actually, they don't take commas. I don't know why I had commas there. That's a typo. And I'm not using time anymore. And I'm going to format this so it looks nicer, and we'll run it again. And I get my output. You know, doing this stuff on the fly, sometimes you get little screw-ups. Pardon my dust. So, in this case, I've created an album variable. The album variable is based on an anonymous struct type. And it's also initialized with a struct literal right here in the code. So, it's actually just fine. I can do this. Now, this is not terribly convenient. And the reason it's not terribly convenient is because let's suppose I have another one. Or actually, right, you know, can I just create a variable? Let's suppose I want to have a variable that's, you know, a pointer to an album. And we'll just give it a PP prefix. I don't like doing that, but I could. So the question is, you know, can I do this? I believe so. All right. Yes, I need to do something with it, so we'll just print it for a second. Ah, interesting. So, if I just print the pointer, it tells me it's an address to one of these. That's kind of interesting. I don't know if I've seen that before. But more importantly, you know, var palbum is fine as long as I initialize it. But suppose I just wanted to create a var palbum of some type, and the answer is I can't, because the only thing I could do is I would have to copy all of this over again, right? And actually, I think I can do that. And of course, now the pointer is nil because I didn't initialize it. So that's rather inconvenient. Most structs are going to be given type names, all right? Well, that's going to get us into this issue of compatibility. Right? Because we have structural compatibility and name compatibility. Now, here I have, let's do one other thing. Let's call this album 1. And just to keep things from running over the page, we're going to simplify our album so it just has a name. And then I'm going to create a second one. And do that. So I have a couple of albums. Now, what if I want to assign them? What is that doing? So two things. First of all, an assignment is a copy. We're going to copy all the data in the struct over. Okay? Number two, this works because of structural compatibility, right? And we talked about this. In a second, I'm going to jump to the slides, but we talked about structural compatibility. Okay, these two structs have the same structure and behavior in the sense that they have the same field names and field types in the same order. And so I can assign one to the other even though they're anonymous types. Okay, now let's go a different route. And I'm going to create two named types. And they're going to have the same fields. And I'm going to initialize them a little differently, of course. Since I'm using a album at 1 and 2 as the types. So the question is, can I do this? All right, I now have created named types for these two albums. All right, Will that work? And the answer is no. Well, it won't work first of all, because I missed that out. Okay, now I got the error I actually wanted. I can't assign A2 to A1. Why not? Because they're not the same name type. As soon as I gave these type names, right, they became incompatible because now we're into named typing. Right? But what I can do is they are convertible. I can convert with a type conversion an A2 to an A1, and that works, and they come up with the same values. So we're back in the slides for a second, and I want to point out the rules, because the rules are they're compatible if they have the same field types and names in the same order, and also with the same tag. Now, tag is something I haven't shown you yet, and we're going to talk about it more in a second, but briefly speaking, there's something else I can have in a struct declaration. All right? And if those things match, they have the same structure and behavior. Okay? I also want to point out here, can I do an equality test on structs? And the answer is, well, so there's two things about a struct. It's an aggregate. It has various fields within it. If the fields are comparable, the struct is comparable. So these structs that have like strings and ints, I can compare them. I can use the equal operator. If I had a byte slice in one of these structs, I could not, because byte slices are not comparable. Okay? And the other question is, and I think we've already kind of seen this, but I'll mention it. What is the initialization of a struct? And at the very beginning, I created this empty employee. And so the zero value of a struct is the zero value of all of its fields, right? So if I have an int field that I don't put something in, it's a 0. If it's a string, it's an empty string, and so on. Okay, and that's all kind of logical. Right. So here's an example of variables, again, were anonymous structs, and I can assign them. Okay, and this is a struct tag. Again, we're going to talk about it in a little bit when we talk about JSON. But a struct tag is a string that's put after the field type, and it has some information about how to encode in various protocols, right? So we can create a key for JSON or other things. And when we look at how JSON works, it's going to use reflection. So the information that's in that little tag, in that little raw string, is kept with the type information, and it's available at runtime for things like the JSON software to use it to know how to do encoding and decoding. Okay, we'll get to that. But that's a struct tag, and it's part of the type definition of the struct. Okay, so in this case, I have one field. It has the name capital X. They match. Struct tags match. They're compatible. I can assign. Okay, these were named types. Okay, name types are not compatible. I can't assign. Okay, they're convertible though. Name types can be converted through a type conversion and then assigned, provided that they would be compatible structurally. In other words, if they have the same fields and the same other things, then I can convert the name type from one to the other, because if they didn't have the name type, they would be structurally compatible. Okay? And what I probably should have here is an example of one that isn't. If I added a field here, if T1 had some other field in it, Y, then they still wouldn't be convertible because they wouldn't be compatible otherwise. You can't assign a 2-field struct to a 1-field struct or vice versa. That just doesn't work. Now, there's one more detail, and this is a picky detail, but I said the struct tag is part of the definition, and so in the past it used to be if the struct tags didn't match, then your type was not convertible. It not only wasn't compatible, it wasn't even convertible. And that changed in Go 1.8. Somebody realized, well, for the purpose of actually just copying the underlying data, we should be able to do a type conversion and ignore the tag, because the tag is sort of an extra piece of data. And so as of 1.8, even if I have different struct tags, but they're otherwise the same field names, same field types, same order, then the type conversion is okay, and we can do that. Okay, so I want to show one other thing really quickly with this next slide, and that is, again, structs are copied. And that means when a struct is a parameter, it's also copied. Well, that's good up to a point, but let's suppose I've got this function sold another, and we pass it an album, and we want to increment the number of records sold. Okay, well this first example has got an oops, because I made a copy of the album, changed the copy, and when I'm done with the function, the original album didn't change. So if we want to modify a struct, we've only got a couple of choices. Either we have to pass it in as a copy and return it as a copy. That's okay, we could do that. We may not want to depending on how big it is, and I'll talk about that a little bit later. But I can also pass a pointer to it and use reference semantics, in which case the A inside of this second sold another is not a copy, it's the original, it's a reference to the original album. Now, notice this little dot notation, all right? One of these was a value, one of these was a pointer, but I'm still using the same dot notation. And if you're familiar with a language like C, you might have expected something like A and a right arrow to copies, because you have a special operator that says access a field of a structure through a pointer. Well, we don't do that. Go is smart enough to know that this is the same as explicitly putting a star. And I could write that. I could write open parenthesis star A close parenthesis dot. I don't need to. Go says I know how to get to a field through a pointer of the same type, and it just does it. Okay, so that makes writing the code easier. It's a little less obvious when you look at this line right here that A is a pointer, but I think that's okay. So I want to go back to an idea we talked about earlier about making the zero value useful. And we talked about it before in the context of things like, you know, a nil slice is safe to take the length, and you can do things with nil maps mostly, right? So how about structs? And it's really useful if you can create a variable of a struct type and have it be immediately usable right as it is. Okay, so I've copied a little bit of text out of this Go programming language book because I think it expresses it well. Okay, that the zero value for a struct is a natural or sensible default for using this type. And one of the examples given is the buffer. So, you know, when I create a buffer variable, is it usable, or do I have to do something to it to make it usable? And the answer is this is a case where it's usable, because the zero values of the fields have been thought out in a way that make them sensible. The zero, I've got my byte buffer inside has a byte slice to represent the actual data. A nil byte slice is usable. I can append to it immediately. So I don't have to already do something to make that work. Okay. The offset is an integer, its value is 0, and probably I want to start reading or writing my buffer at offset 0, so that makes sense. And this third thing is a sort of enumerated type. Go has a particular way of doing that. It's not exactly the same as in a num. But anyway, the default value or the zero value of a read op has been chosen to be like an invalid operation. So again, it's a sensible default. So if you just create a buffer variable, you can immediately do something with the buffer variable, and it's going to be logically safe for the various operations you'll do on it. And I think that's, again, a really neat idea. It's not going to always be possible. Okay? If buffer were a map, this would never be possible, or probably never be possible, because you could do certain things with a map, but you can't put a key into a map unless you make it. So maps make this a little harder in the sense you got to make the map somehow, right? And if you do go down that road, then you're more likely to have some function new buffer whose job it is to make sure the map gets made and then return you a buffer that's ready to use. Okay, but whenever possible, we'd like to avoid the new buffer and just be able to create a variable of the struct type and just have it just work. So there's one more little thing, and it's kind of a pun, because I can have something that's a struct with no fields. How small is it? It's invisible because it takes up no space. And so some folks will use that creatively. You know, one way to represent a set, because Go doesn't have a set type of its own, is a map of something to bool, but you could also do it as a map of something to an empty struct. It takes up a little bit less space. I don't know that it's actually better. Okay. We haven't talked about channels, and channels are something we'll talk about in concurrency. I may or may not need to actually pass data through a channel. It may simply be enough to have the channel, in which case I can create a channel of empty struct. And there's no space required. Now, an interesting thing about the empty struct is it's a singleton. If you've seen one empty struct, you've seen them all, because there's no way to differentiate two different structs that have nothing in them. Okay, and actually Go keeps a variable of type struct with empty brackets in your program somewhere. There's a particular place where that guy lives as a singleton. And if you go back and look at what an empty slice is, an empty slice actually had a pointer to that. That was the sentinel value used in an empty slice to differentiate from a nil slice. It has the address of the empty struct because it's always in the program because it's a singleton. Just curious, you know, it's trivia, Go trivia for you. Okay, so now I'm going to move on and talk about how we do JSON, and I'm going to do it particularly in the context of structs, because that's the most interesting thing. So I'm back in the playground, and we're now looking at, I've got a struct type, and I've given it some struct tags. And again, a struct tag is a raw string in backticks, okay, and it has a certain standard format. The first thing is you have some sort of keyword followed by a colon. Now Go doesn't prescribe what the keywords are. Only some of them are actually going to make sense, right? There's a library to do JSON, and it knows how to read keywords that start with JSON. There's stuff for doing databases, and it knows how to read a keyword with DB in front of it. All right. If I put a keyword XYZ, well, it's going to be there. It's not going to do anything because I don't have an XYZ library to do translations. And struct tags are mostly used for doing conversion of data in the program to an external format. Okay, JSON, XML, ASN.1, and so on. Okay, proto-buffers. Okay, SQL database stuff. Right, so I'm usually using them to move data between Go and some outside world, and I'm doing that by using stuff that encodes and decodes with reflection, because through reflection it can say, hey, I can look up this type. So you give me a variable of type response, and I know how to figure out what the fields are and how they should be represented in JSON by going and reading the struct tags. Okay, now if I look at the struct tag after the colon, then I've got an actual string in quotes. And that's one of the reasons we use backticks for struct tags, so I can have these embedded quotes and not worry about it. And the first thing here is page just says, hey, when you produce this object in JSON, the property name is going to be page with a lowercase p. Okay. The second one's more interesting because I've also got a comma and a second little thing. This second tag says, don't put this in if the field is empty. Okay? And so we'll see how that actually works out in practice. I'm going to create a response, and for right now, it's got a page number and it's got some words on the page. Okay, if I print that, okay, no surprise, I get a structure that represents the page and the words. I did it with #v, so you see all the gory details. Okay, but what I want to do now is I'm going to pull in another package. The JSON encoding package. And most of these live under encoding, so encoding/JSON or XML or whatever. Okay, and that gives me access to a function like JSON.Marshal. All right. And I'm going to print out what comes back. Now, there's a trick here. Actually, there's two tricks. First of all, I'm ignoring the error, okay, for teaching purposes. But Marshal is going to return me a byte string because typically we're going to send this stuff out. I'm going to create JSON because I want to shove it out a socket or write it on disk. So it gives me a byte slice, and I can't really print that. Or if I did, you'd see a whole bunch of numbers. Okay, so let's print it. And what I get is proper JSON. And if you were looking at the screen, it went from the internal representation, which maybe I should have left that there. Okay, clearly need to think through a little bit more, but if I left that there, right, we'd see the JSON and the internal representation. The internal representation is not JSON. We don't quote the keywords and so on. But if I look at the JSON, right? It has a property page, lowercase p, and a property words, lowercase w, and it actually has a proper JSON array of string values with quotation marks and commas. So it produced JSON. Great. Now, we're going to undo that, which is to say, and then we'll print that. Now, JSON.unMarshal takes into it a byte slice. Again, we typically were decoding stuff from the network or somewhere, and it takes a pointer to a place to put it. Okay, so we have to give it the address of R2. If we don't give it the address, it's not going to work because it's not going to be able to get to R2. So we give it the address of R2, and we're ignoring the error again. And then we'll print out R2 after we get it. Okay, and now, the only difference here is when I created R up here, I gave it an ampersand. I went ahead and made a pointer to it. I don't have to do that. And now I see that my R and R2 are exactly the same. Okay, they print out the same way, right? It doesn't really matter that I created a pointer and passed it in. It's not going to change anything. Fine. So I've encoded and decoded some JSON. Now I want to show you the purpose of emit empty. I want to go back here and I'm going to take out this part of my initialization of my response. So now my response has a page. It doesn't have any words. And when I run this, my JSON's not going to have any words either, right? So the function of emit empty, it says, oh, your slice is not got anything in it. So just don't put out that property name. So I get a JSON object with just the page property and not the words property. And, you know, down here my words are nil. Okay, if I didn't do that, the alternative would be I'd have words, but the words would be a JSON null. And that's a choice. It depends on how you want to represent yourself to the outside world. My real purpose was showing that you can have additional tags in here. So even for JSON, you can have more than one thing, not just the property name, but something else. Now, here's a question for you. Why do I have to have these property names? Well, now, and this is my personal preference, I like JSON with properties that have lowercase letters. Okay? Not everybody does, but I do. And so, if you look at my response structure, my field started with an uppercase letter. Okay? Now I'm doing that to make them exportable. And in theory, in my program, I may want them to be exportable just so how my program can use them. But this is very important. Okay? If the variable starts with a lowercase letter, if the field name in the struct starts with a lowercase letter, it's not exported. And if it's not exported, JSON will not encode it. Okay, and so now if I do this, okay, well, first of all, I get a result. Okay, so there's two things going on in this little display. This is neat. I want to talk about this. The first is I get my JSON and it doesn't have words. It doesn't have words even with null, and I didn't do an omit empty, right? But I didn't export the words field from the type. Okay? It has a lowercase w, not an uppercase w, and so from the purpose of doing any of these encodings, it just disappears. Okay? Private fields of a struct that are not exported are not encoded. So what's the other neat thing going on here? When I ran this program before compiling it and running it, the Go Playground now runs a tool called GoVet. And GoVet is a static analysis tool, also known as a linting tool. And this tool, so the compiler doesn't complain about the program, but GoVet gives you a warning. And it says, hey, you have a struct tag for JSON that doesn't do anything because you didn't capitalize the W in words, and so the field is not exported. And that's very good. So this is the kind of thing you get out of static analysis, right? the program is correct from the point of view of the compiler, but it's got something that's probably a mistake. It's not what you intended, to have an unexported field but a struct tag. And so you get this little notice from GoVet saying, hey, go look at this. And the fact that we have these tools is incredibly valuable. It gives us a lot more confidence in our code before we even start to run it. So I want to drop back into the slide for a second. I'm not going to try to demonstrate this because I don't think I can do any kind of database stuff from the playground. But I can also use struct tags for databases. And so if you're doing SQL, for example, from Go, right, I can create structs. I can put struct tags. Let's start with something like DB instead of JSON. And then I can do some kind of fancy things with an SQL statement and automatically have it properly marshal the data into the statement. Okay? Now, if you know anything about security in SQL, you've probably heard the word SQL injection, or you've seen the very neat little cartoon about little Bobby tables. All right? And the way you avoid this is you never build up SQL by just writing string operations. You want to use stuff in a package that knows how to build up your SQL statement properly in a way that guarantees you don't get the little Bobby tables effect, right? That somebody can't do SQL injection and delete your database. All right, and the struct tags also make this convenient. It's a very convenient way to do this. Okay, so that's what I wanted to say about structs in JSON. Now, I think there was some other example I gave where I showed encoding slices in JSON. You can marshal anything in JSON. I did this JSON part in the context of structs because that's a very common use. We want to have JSON objects. It is, after all, JSON JavaScript object notation. And we represent those JSON objects as structs most often. And we have a neat way of annotating the struct with struct tags to help convert the JSON back and forth. And of course, that came in the context of explaining how structs work in Go.